when she was a PhD student in Cambridge, I guess, or just finished. She finished in 2004. Her advisor was James Norris. And then from there, she went to Paris 6, I guess, with Jean Berton. And she then went to Warwick, and now she's a full professor at Oxford University. She has a medallion lecture in IMS in 2017, I guess, no, 16, and she's a fellow of IMS, Institute of Mathematical Statistics. It is a real pleasure to listen to her in this colloquium. She will talk about random trees, I guess, and critical random trees. So, Christina, please.
Pablo, thank you very much for the very kind invitation. It's lovely to be here. I would obviously much rather be in Buenos Aires itself, but this is what we have to make do with at the moment. But it's lovely to see so many of you here. So I'm going to be talking about things which are related to random trees, but the title of my talk is The Critical Random Transposition Random Walk, and you will see in a moment why those things are related, or possibly a little bit longer than a moment. Can I just check that everyone can hear me and that you can see me fine and that my slides are moving okay? So what is the random transposition random walk? So let me start by telling you that. So this is going to be a continuous time random walk on the symmetric group Sn. So I'm going to start from the identity permutation, and then at rate n on 2, I'm going to compose whatever the current state is with an independent uniform random transposition. Okay, so at every stage of this process, I've got a random permutation, which is gradually having new transpositions composed with it. Okay, so I'm starting from the identity permutation here, and I'm just going to one by one compose with uniformly chosen transpositions. Maybe 1, 2 wasn't very uniformly chosen, but anyway. And I'm going to immediately draw a picture which has a little bit of extra structure. So whenever I include a transposition, I'm going to include the edge between two vertices which have the labels of the transposition. So, and I'm going to try and keep the order in which I apply them. So A indicates that this was the first one, the next one will be B. Okay, so the next transposition I compose the state with is 3, 4. And I'll try and keep my state in cycle notation here. Okay, so for the moment, not very much interesting has happened. If I compose, say, with 1, 4, then what happens is I've got these two little cycles, 1, 2, and 3, 4 here, and they get joined together. Okay. So 6, 7. I'm just going to run through this example because I think it's quite important to kind of get the idea and maybe the picture as well is helpful. Suppose now the next transposition to arrive is the transposition 1, 3. So that's going to affect this cycle that I have here. And indeed, the effect that it has is to split it, in fact, into 2 cycles, one of which is the fixed point 3, and the other of which goes around the outside here. Okay, so let's just see how that arose. So what happens now to 3? Well, it gets flipped by the second transposition that arrived, B, to the position of 4. Okay, and then the next transposition which arrives flips it to there, to 1. And then finally, transposition E sends it back to its starting point. So I like to think of these things as having numbered counters which start on the original points of my picture and which get moved around by the transposition. So here, the original counter, which has label 3, first moves to this position, then to that position, and then back to its original starting point. That indicates that 3 is a fixed point of this particular permutation that I've got to. Okay, please don't hesitate to interrupt me if there are any questions or if anything is unclear. Okay, so one thing that's relatively easy to show is that this Markov process has as its stationary distribution simply the uniform distribution on the symmetric group. So that's a relatively easy exercise. And my main interest is going to be in the lengths of the cycles of this dynamic permutation that I'm building up. So just to fix some notation, if I give you an arbitrary permutation pi, let me write C1 of pi, C2 of pi, and so on for the lengths of the cycles written in decreasing order. So C1 of pi is the length of the longest cycle. And I first want to talk about this for the stationary distribution itself. So the stationary distribution, the uniform distribution on the symmetric group. Okay, so if I take a uniform random permutation of the integers 1 up to n, and I write it in cycle notation and list the cycles in increasing order of least element, what can I say about the lengths of those cycles? This is quite a classical topic, but in any case, I want to just go through a few of the details. So let me ask, what's the length of the first cycle? Okay, so there's a nice approach to this question, which I think maybe dates back to William Feller, which goes as follows. If I start from the label 1, okay, so then the place that that gets permuted to, so pi n of 1, is just chosen uniformly at random from the possibilities. So it could be that 1 is a fixed point of the permutation, in which case 1 gets mapped to itself, but it could also go anywhere else, and it's equally likely to be any of those possibilities. So I am going to have a fixed point, or I'm going to close the cycle with probability 1 on n, and otherwise 1 gets mapped somewhere else in my permutation. Suppose that I didn't close the cycle at the first step, so 1 got mapped somewhere other than 1. Okay, so then the next thing, so pi of 1 is chosen uniformly at random, but now from the set of the first n integers, but remove from that the place pi n of 1. And in that case, we're going to close the cycle, we map back round to 1, with probability 1 on n minus 1. So if you continue this reasoning, at step k, conditionally on having not yet closed the cycle, I'm going to do so with probability 1 on n minus k plus 1. And so in particular, we can work out what the length, or what the distribution of the length of this first permutation cycle is, the one that contains the value 1. So the probability that I get exactly length k, well, I have to have not closed the cycle on the first step, I have to have not closed it on the second step, and I have to have not closed it on all of the steps up to k minus 1, but then I do need to close the cycle on the kth step. And this nice product here just telescopes, and I get left with just 1 on n at the end of the day. So in particular, that tells me that the first cycle has a length which is simply uniformly distributed on the first n integers. Okay, so it could be 1, could be 2, all the way up to n, and it's equally likely to be any of those possibilities. And a convenient way to write this is just to say that it has the same distribution as what I would get is if I took a uniform random variable on 0, 1, a continuous uniform random variable on 0, 1, multiply it by n and take the ceiling, the integer above. Okay, another thing we can get out of this is that conditionally on the elements that happen to be in that first cycle, the rest of the permutation is just a uniform permutation of the remaining elements of the first n integers. And so in particular, that tells us that we can actually write down the distribution of all of the cycle lengths. So we've got this first one, which is uniformly distributed on 1 up to n, okay, which I've chosen to write in this particular way. And that leaves me with a number n minus that of elements. And the next cycle then just takes up a uniform number of those. Okay, so I again obtain that by taking this integer here, multiplying it by an independent uniform random variable on 0, 1 and taking the ceiling, and so on and so forth. And that makes it very easy to see that if I rescale these cycle lengths by 1 on n, so what I'm saying is that the cycle lengths are tending to have size on the order of n. So if I rescale away that n, what I'm getting is convergence in distribution to a sequence which looks like this. So I take a uniform. So this is sometimes described as a sort of stick breaking construction. I've got a stick of length 1. I break it at a uniform place. That gives me the length of the first cycle. And then the remaining length of stick, which is 1 minus u1, I then break that at a uniform place. And then I'm left over with another bit. I break that at a uniform place, and I keep doing that. And that gives me these limiting cycle lengths for a uniform random permutation. If I want them in decreasing order, I'm allowed to do that. I can simply say, well, let's take this thing. It's not a priori in decreasing order, but I can just put it in decreasing order. And this has a name. This distribution is the so-called Poisson Dirichlet distribution. And that's going to play quite an important role in the rest of my talk. Okay, so this is what happens for the stationary distribution for my random transposition random walk. So the stationary distribution is just uniform on the symmetric group. And if I look at the cycle length in decreasing order, then they converge in distribution as n goes to infinity. So if I look at a large random uniform random permutation, what I'm seeing is cycle lengths which have proportions given by this Poisson Dirichlet 0, 1 of the amount of numbers in them. Okay, so the uniform distribution for the random transposition random walk is stationary. And indeed, it's the case that there exists some random time, which turns out to look like a half log n in the time scaling I've taken, which is known as the mixing time, which is such that whenever I'm beyond that time, in fact, the state is looking pretty much like it's in stationarity, right? So in particular, if I look at the rescaled cycle lengths in decreasing order, I'm seeing something that's close to Poisson Dirichlet 0,1 in distribution for large n. I don't want to try to make this statement any more precise because we'll just get into sort of technical fiddling, and I think that's not really the point. The point is just to understand that there's a time which is about log n beyond which we're typically seeing something like the stationary distribution. One thing that's very interesting about this process, though, this random transposition random walk, is that there's a celebrated result of Oded-Schramm, which says that this Poisson-Dirichlet distribution actually turns up a long time before the mixing time. And let me just take a few slides to describe Schramm's results to you. So what Schramm's theorem says is that, in fact, if we look at times on the order of 1 rather than on the order of log n, and specifically, if I look at times which are smaller than 1, then the longest cycle in my random transposition random walk is only logarithmic in n. And something very dramatic happens at t equals 1, so that if t is bigger than 1, then there exists some random set an of t, which is macroscopic in the sense that it contains a positive proportion of all of the numbers 1 up to n, which is such that if I take the ordered cycle lengths and I rescale by the size of this set, then I'm seeing convergence in distribution already to Poisson-Dirichlet 0,1. Okay, so let me try and unpack that a little bit because it's quite a lot to take in one go. So what I'm saying is that there's some subset of the numbers 1 up to n, where if I just sort of look at the permutation restricted to that subset, already I'm seeing something that's basically stationary. Okay, so this value theta here, in fact, is known, it's deterministic, and it's just the smallest non-negative solution to this equation. So we even know what proportion of the numbers 1 up to n are sitting in this kind of special part of the state space, which is somehow already mixed. So we should think of this Poisson-Dirichlet distribution as really representing we've achieved stationarity in that part of the set. Okay, so Schramm has a very beautiful proof, which I'll tell you some details about, but I also want to mention that there's a simpler proof due to Nathanael Beresticki if you just want to know that there are macroscopic cycles for t bigger than 1. Okay, so a key point in the proof of this theorem really is a coupling with the so-called Oded-Schramm random graph GNP. So what do I mean by the Oded-Schramm random graph? I mean, take n vertices, and for every pair of those vertices, I'm just going to independently join them by an edge with probability p, or not join them otherwise. Okay, so how might one build up a relationship between the random transposition random walk and an evolving graph? Well, I've actually already shown you on the picture, but let me make it explicit here in words. So I'm just going to take, so we had Pn of t was the state of the random transposition random walk at time t. So let Gn of t be the related graph. So this is the graph whose vertices are labeled by the integers 1 up to n, and whose edges are given by the set of pairs ij, such that I've applied the transposition ij in the construction of my random transposition random walk. So whenever a transposition is applied in P, I'm just going to include the corresponding edge in the graph. So just a quick back of the envelope calculation, the state is changing at rate n on 2. That was the way I set things up. So I'm applying a new transposition at each rate n on 2. There are n choose 2 possible transpositions, so n minus 1 on 2. And so that means that each individual transposition is arriving at a rate which is given by 1 on n minus 1. Okay, so you can think of, associated with each edge of your graph, you've just got a little clock, which is, the alarm clock is sort of ringing at rate 1 on n minus 1, and that's when that edge arrives. Okay, so in particular, that tells me that the probability my edge has already arrived by time t is just the probability that an exponential 1 on n minus 1 random variable has rung, or my alarm clock has rung by time t. And the probability of that is 1 minus e to the minus t on n minus 1. I'm going to be thinking of n as something very large here, but so I'm just going to straight away approximate 1 minus e to the minus t on n minus 1 by t on n. Okay, that's going to be a convenient approximation to take. And rather a lot is known about the Euler-Schreier random graph in precisely this time range, if I can put it that way, this parameter range. So if I take gn t on n, let's call this t on n, then there's a theorem which dates back to the work of Euler-Schreier in 1959, which shows that this graph undergoes a phase transition around t equals 1, which is precisely what we were seeing in Schramm's theorem, that t equals 1 was playing a key role. So in particular, if t is less than 1, so I've got the probability that a particular edge is present is looking like t on n, okay, and there are n choose 2 possible edges, okay. So if t is less than 1, the largest component of this graph, the largest connected component, has size which is logarithmic in n. If t equals 1, there's a sort of intermediate size scaling where the largest components have size on the order of n to the 2/3. And then importantly, as t gets bigger than 1, there then exists a unique, so what we call a giant component. So that's a component which contains a positive proportion of all of the vertices. And this proportion is this theta t thing that we've already seen, which solves this, which solves this equation here. Okay, so there's a unique component which is giant in the sense that it contains a proportion theta of t of all of the n vertices. And all of the other components are much, much smaller. They're at most logarithmic in size in n. Okay, so the probabilists in the audience will probably recognize this quantity here as being the survival probability of a Poisson T branching process, and that's not a coincidence. There's a nice approximation theorem essentially that tells you that the small components look like branching processes. Okay, so how do I get from this theorem for the Euler-Schreier random graph, which has been known for a very long time, back to Schramm's result for the random transposition random walk? Okay, so here's the key fact. Any cycle of the permutation is wholly contained within a component of the graph. And this is where I hope this picture is helpful, because I've drawn both the graph and the permutation. So here we've got an instance where we've got a component of the graph, which consists of the vertices 1, 2, 3, 4, which actually contains 2 different permutation cycles. Okay, so there's this cycle here, which is just 3 maps to 3. So the fixed point of the permutation. And then there's the cycle that goes around the outside, which goes 1, 2, 4, and then back to 1. Okay, so it's not necessarily the case that the vertex sets of the components are the same as the vertex sets of the cycles, but any cycle is contained within a unique component of the graph. And so in particular, the components give you an upper bound on the potential sizes for the cycles. Okay, so since in the case where t is less than 1, the subcritical regime, you might say, since the largest component is order n, even if all of that component were contained in a single cycle, that would still only give you log n for the length of the cycle. So that easily gives you the result that Schramm claimed for t less than 1. For t greater than 1, it's much more complicated. So we know that there's a giant component whose vertex set is this ATN, which has got size macroscopic in n. Right, so it's got some size which is looking like theta of t times n. But the point is that necessarily any macroscopic cycles, any cycles which have lengths on the order of n, they must be contained within that giant component somehow, because all of the other components we know have size at most logarithmic in n. Okay, too small to contribute on this scale. So roughly speaking, and I hope to sort of go into this a little bit more in the next few slides, it's the dynamics on the giant component which are producing these Poisson-Dirichlet 0, 1 relative cycle lengths. So we have to sort of restrict our attention to what's going on in the giant component, and somehow the dynamics are giving us this Poisson-Dirichlet 0, 1 kind of signature of uniformity. Okay, so let's think a little bit about what the dynamics are doing. What happens when I compose with a new transposition, which I can think of as adding a new edge in the graph? So I have a collection of cycles which are sitting in my permutation, okay? And if I introduce a uniform random transposition, what's happening is I'm picking 2 permutation cycles, right? Which are picked with probability proportional to their size. I'm more likely to pick a permutation cycle that's larger. Okay, it might be that I pick the same permutation cycle twice. There's no reason why not. I'm just picking 2 points and they might both land in the same permutation cycle, or I might pick 2 different permutation cycles. If the cycles are distinct, adding the edge merges those 2 cycles into a larger cycle. And on the other hand, if they were in fact the same cycle to start with, it has the effect of splitting. Okay, and because everything is very uniform, in fact, it splits at a uniform point in the cycle. So what I'd like to do is give you a sort of idealization of this process that doesn't any longer have the integers 1 up to n involved, but which is a sort of continuous version of it. This is sort of what I want to imagine is going on if I take the limit as n goes to infinity and I rescale everything by n. Okay, so somehow the natural state space for this process is ordered sequences whose sum is 1. So ordered sequences of non-negative real numbers whose sum is 1. And somehow here is the continuous version of what's going on inside this process. Really at rate 1/2, what I'm doing is I'm picking 2 independent size biased picks from among the blocks. If those blocks are distinct, I'm merging them. And if on the other hand, I happen to pick the same block twice, what I'm really doing is splitting it apart in a uniform way. So 2 blocks which have relative sizes uniform and 1 minus uniform times whatever the original size of the block was. And just for definiteness, whenever I've done one of these jumps, what I'm going to do is I'm going to resort the blocks of my, my sequence into decreasing order of size. Okay, so there's a theorem which is due to Diaconis, Mayavov, Tsaiduni and Serna from 2004, which says that the Poisson-Dirichlet 0-1 distribution is the unique invariant distribution for this split merge dynamics. So that tells me that if I run this, this dynamics sort of forever, then eventually I'm going to end up with the Poisson-Dirichlet 0-1 distribution as what I see. Okay, so here's the heuristic for the random transposition random walk. Once I've got to the stage where there's a sort of macroscopic number of points which are connected, once I've got to the stage where I have a giant component, then the split merge dynamics on that giant component is mixing faster than newer components are getting joined onto the giant. And since Poisson-Dirichlet 0-1 is stationary for these split merge dynamics, and that's what I'm applying within the giant component, that's what I'm seeing. So essentially, I've got 2 different timescales in operation. There's a timescale for what's happening in the giant component, and that's mixing very fast to give me this Poisson-Dirichlet 0-1 thing. And then there's a sort of slower timescale on which, you know, small bits of mass are gradually getting added onto the giant and then getting mixed in with things. So that's sort of the explanation for why we're seeing this Poisson-Dirichlet 0-1 on part of the state space much earlier than the mixing time. So for the rest of the talk, I'm going to concentrate on what's happening at t equals 1, or t is roughly equal to 1. So this is the point where in the Heuristic picture, so if I look at the Heuristic random graph GNT on n, if I take my t to be, well, let's say 1 or slightly more or less than 1, so it turns out there's something called a critical window during which you see the same sort of scaling behavior. So if I take 1 plus lambda n to the minus 1/3, then throughout this range, the largest components of the Heuristic random graph have this intermediate size. They're not yet giant, but they're bigger than the sort of logarithmic ones we see in the subcritical regime. And in fact, they're on the order of n to the 2/3. So I'm going to refer to this as the critical window. And a question which I think dates back to Heuristic, and I know that Nathanael Heuristic also asked it, what precisely happens to the random transposition random walk in this critical window? So this is somehow the point when the action is beginning to occur, and we'd like to have a nicer description of how we're getting from the subcritical regime to the supercritical one. Okay, so the critical window for the Heuristic random graph is a rather well understood thing. I'm just going to spend a couple of slides summarizing some results of David Aldous, which tell us what the critical behavior for the component sizes of the Heuristic random graph are. Okay, so I'm taking my graph which has n vertices and where the probability for any given edge that it's present is looking like 1 on n times 1 plus lambda times n to the minus 1/3. Okay, so here's the theorem which is due to Aldous, which says that if I take the component sizes I list them in decreasing order. I rescale by this n to the minus 2/3 factor. Then I get convergence in distribution to some random sequence, which lives in the space, which I'm going to refer to as L2 down arrow. So this is just the space of square summable sequences, which are ordered largest to smallest. So let me tell you immediately, so Alders's theorem tells you slightly more than this. It tells us exactly how to obtain this limit sequence here. And that's as follows. So I'm going to start with a Brownian motion, which has been given a parabolic drift. So I've given it a drift, which is lambda t minus t squared on 2. So if lambda's positive, this is sort of initially positive, but then gradually gets more and more negative as the t gets larger. Okay, and lambda might be negative to start with also, that's also possible. So this is something which is eventually going to drift to minus infinity. Okay, so I need this drifting Brownian motion, and also I need to keep hold of its running infimum. So what's the minimum or the infimum I've seen up until time t. Okay, so the first thing I do is I reflect Brownian motion in its infimum. Okay, so I'm just going to take Brownian motion, subtract off its infimum, and that gives me something which is always positive. Okay, and it looks a little bit like this. And I want to let these zeta 1, zeta 2, and so on, these are going to be the ordered lengths of the excursions of this process above 0. So this process is such that there's a collection of open intervals during which it's away from 0, okay, sort of bookended by points when I'm at 0. And it turns out that it makes sense to order those excursion lengths. Okay, so I can put them in decreasing order. There is a longest one, and they're also square summable. Okay, and so the theorem says that if I look at that list of ordered excursion lengths for this Brownian type process, then that gives me the limit in distribution of these component sizes for the Euler-Schwendimann graph. So I think probably looked at like this is going to look slightly surprising. What has a Brownian motion got to do with a random graph? I unfortunately have too limited time to be able to really go into the details of this. But let me just say that this is a very beautiful paper and something that is well worth looking into. So that's sort of telling us what's happening at a fixed point in the critical window. But we're also interested in dynamics. What happens as we move from, say, negative lambda to positive lambda, or what happens as I increase lambda and I move through this critical window. So remember that what's happening in the graph is that gradually edges are arriving. So in particular, if I've got two components which have sizes x n to the 2/3 and y n to the 2/3, then the number of possible new edges between them is just x times y times n to the 4/3, okay, because I've just got as many edges as there are products of points here, okay? And each of those edges is arriving independently at rate n to the minus 4/3. So in other words, what's happening is these two components are getting merged at rate x times y. Okay, so it turns out that you can make sense of this in the limit. So if I think about the process of component sizes as lambda varies, then I can think of a limiting process here, which is indexed by my position in the critical window, where the dynamics of this process, so this is called the standard multiplicative coalescent, the dynamics of this process are that we're getting that blocks of this process will merge, and blocks of sizes x and y merge at rate x times y. Okay, so you can also ask the question, what's happening as the lambda gets very large? So it's clear that the blocks are coalescing, right? Over time, the largest block is getting larger. And it turns out that, and this is something we expect to happen because we know that sort of beyond the top of this critical window, we're seeing the emergence of a giant component. It should be that eventually one block dominates. Okay, and that is indeed the case. The largest block, if I think about it as a process in lambda, turns out to behave a little bit like 2 times lambda. And on the other hand, all of the other blocks are behaving on a smaller scale in lambda. So as lambda goes to infinity, the second largest block is vanishing once I rescale by lambda. So this is really this, things are getting more and more squished together, and gradually there's one block which is coming to dominate everything else. So that's the multiplicative coalescent, which is describing somehow the dynamics of the block sizes in the Heuristic random graph. Let me just emphasize something, which is that the space we're living in here is this L2 space, right? So we have square summable sequences, and in particular, these sequences are not themselves summable. So I need to take the square in order to get something finite in sum. Okay, suppose now I turn to the random transposition, random walk. So we described the basic dynamics a little bit earlier. We have this sort of split merge thing. So when a new transposition arrives, it either merges two cycles or it splits a cycle in two. Now, the merging part of that really is just this multiplicative coalescence that we have in the graph. It really is just, I've got probability, I've sort of got rate x times y of having two cycles merge. But the splitting dynamics, of course, is something extra. So in particular, we can make sense of a sort of candidate limit process here, which has the following properties. So firstly, it's taking values in this space of ordered square summable sequences, and which is such that sort of informally blocks of sizes x and y are merging at rate x times y, but a block of size x is splitting at rate x squared on 2 into blocks of sizes x times uniform and x times 1 minus uniform. So we've got a sort of, we've got a dynamics which is causing the blocks to get sort of bigger, but we've also got a countervailing dynamics which is causing blocks to split apart. Okay. And again, let me just say that for definiteness, once, once something has happened in this process, I'm going to resort the state into decreasing order of size, just so that I know what I'm doing. Okay, so the first theorem that I should have said right back at the start, and it was stupid of me not to have done this, is all joint work with my former PhD student, Dominic Yeo, who's currently a lecturer in Oxford. So our sort of first result is that there exists, firstly, a sensibly well-defined split merge process taking values in this L2 down arrow space, which is such that in the Skorohod sense, we get convergence in distribution of the whole process of the cycle lengths of the random transposition, random walk throughout the critical window to this limiting process. Okay, so for the moment, this looks very abstract. There exists a thing which acts as a limit in this setting. So let me at least tell you one thing about it. So I'm going to give you a slightly more sensible description of its marginal distributions in a moment, but the thing that's sort of maybe most key about this is that in contrast to the multiplicative coalescent, where we get one block which is sort of gradually dominating, in this setting, if we rescale in the same way by 1 on 2 lambda, and we look at the sizes of the blocks, we're getting convergence in distribution already to this Poisson Dirichlet 0,1. So that's telling us that this effect that we see in the supercritical regime, whereby on the giant component we're getting sort of Poisson Dirichlet 0,1 cycle lengths, this is already present at the top of the critical window. So really in the phase transition, we already see this Poisson Dirichlet 0,1 coming out as we approach the top of the critical window. Okay. So the critical random graph is a well understood object, as I hope I've convinced you. So the main point in the proof of this theorem is to try to understand a bit better the relationship between the structure of the graph and the structure of the permutation. And one thing that I hope is clear is that it's sufficient to consider the different components one separately. So a component of the graph contains one or more permutation cycles, but the different permutation cycles sit in different components in general. So a couple of key facts which are going to be useful to us. So suppose I see a component of this Heuristic random graph which has a given vertex set, and I know it has E edges. So then it's uniformly chosen from the set of possibilities. Okay, there's no reason why in the sort of description of the Heuristic random graph, there's no reason why one of the possibilities should be more likely than any of the others. So it's uniform. And also conditionally on the component, what order did its edges arrive in? Well, again, there's a lot of symmetry here. Those edges arrived in a uniformly random order. So it's going to be helpful for me to sort of just abstract away part of this. So let me get rid of the sort of randomness in the graph component and just think about a fixed graph component with a uniformly random order on its edges. Okay, so let's let, for a finite connected graph G, let's let pi of G be the permutation which I obtain by applying these transpositions which are represented by the edges in a uniformly random order. And let's see what that gives us. So just a bit of terminology, the surplus of a connected graph is given by the number of edges minus the number of vertices plus 1. So this is a quantity which is always non-negative. It's 0 for a tree because a tree has n minus 1 edges if it has n vertices. Okay, and if G has surplus 2 or more, we call it complex. So you can think of the surplus as just being a measure of how far away are we from being a tree. How many more edges do we have than a tree would have? Okay, so let's first deal with the surplus equals 0 case, so a tree. Okay, so this is a theorem due to Dinesh in 1959, which is that, he didn't phrase it quite like this, but a tree always gives rise to a single permutation cycle. So this is kind of proof by picture, if I can put it that way. I hope that the picture is sort of reasonably descriptive here. Let's just see what happens. So what I want to do is I want to think of a single counter which has the label 7 on it. And I want to see what happens when I apply the permutation so I apply these transpositions, which are coded by the edges here, in the order given by A, B, C, D, E, F. Okay, so 7 sits here. So the first thing that arrives is this transposition A, which swaps the counter here with the counter here. So I end up here. Okay. Then the transposition represented by B is applied, but that doesn't affect me because I'm over here. And then the transposition coded by C arrives, and that sends me out to here. And then none of the other transpositions have any effect on me. So the final resting position, if I can put it that way, of 7 is here over at 6. So that's what this arrow is representing. That's where I end up. And similarly, 6 ends up going down here, 1 ends up going here, and you can see how it works. Okay. So I hope that's reasonably convincing that a tree is always going to give rise to a single permutation cycle. Okay, so nothing very much interesting happens there. If I see a tree component in my graph, then I know that it corresponds to a single cycle whose length is just the same as the size of the tree. Okay, so maybe the next most complicated thing to think about is a graph cycle. So one of the problems with this, we're finding writing this paper, is that there are too many things which have the name cycle. So I'm going to try to keep cycle for cycle of a permutation, and I'll try to use the word graph cycle for a cycle in a graph. Okay, so here's the lemma. So if I've got a graph cycle of length m, so here m is 8, then the associated permutation has precisely 2 cycles. Okay, so how can we see this? Well, let's think about starting here at position with the counter that sits at 8. So A arrives and flips it to here. And then some other things happen which don't affect me until E arrives and flips me to here. And then G arrives. And then nothing else has the sort of power to affect my position. So I end up at 7. And it's not too hard to convince yourself that there are some counters which move clockwise and some counters which move anti-clockwise. Okay, and so the 2 cycles are precisely this partition into who moves clockwise and who moves anti-clockwise with this particular drawing. Okay, so there's always, every time I apply a transposition, I'm really swapping 2 counters. So one is moving right and the other is moving left. Okay, so that essentially tells you in this situation that you're going to have 2, only 2 permutation cycles. And interestingly, there's a sort of concentration phenomenon here. If I took a uniform permutation of the edges, then the lengths of the 2 cycles, so each of the 2 cycles contains a positive proportion of all of the vertices, and indeed that proportion is a half in both cases asymptotically. Okay, so that's a sort of nice simple example. The chance of seeing one of these in a critical Erdős-Rényi random graph is pretty low, or at least there's a relatively small chance of seeing one that's kind of on the order of n to the 2/3. Really, what components with a single cycle look like is much more like this. So they have the sort of cycle, and then they also have what we think of as pendant subtrees. So this is a much more typical picture of what a unicyclic component or a component of surplus 1 would look like. Okay. So you can see that this is somehow an average of the 2 previous examples. So in that I've got little trees which sort of seem to have a single cycle in them. And then I've also got this sort of this graph cycle here, which is doing something similar. So it turns out that there are always two cycles in this setting, and each pendant subtree belongs either entirely to one or entirely to the other of the cycles. So, and that's certainly true for my picture. So here I've got a pendant subtree which is entirely contained in this sort of outer cycle of the permutation, and here's a pendant subtree that's entirely contained in the inner cycle of the permutation. Okay, so what can we say here about the proportions in the two cycles? Well, here things get a bit more interesting in that we have again a sort of scaling limit for this thing. We have again that the two cycles each contain a positive proportion of all of the vertices, but we get a random limit this time, which happens to have the distribution of an ordered beta 1/2 pair, if I can put it that way. So if I take a beta random variable, 1 minus that beta random variable, and then put them in decreasing order, then I get the same thing here. So I want to just say a few words about how that arises, because it's kind of more or less typical of the rest of our results. So the first thing I want to do is tell you some structural facts about a random unicyclic graph GM. Okay, so I've got a graph which is connected, it's on m vertices, and it has precisely one cycle. Okay, so if you pick one of those uniformly at random, then it turns out that the cycle itself, this part, contains a vanishing proportion of the vertices. In fact, it only contains order square root of m of the vertices. So in fact, sort of all of the vertices, to a good approximation, are actually hanging in these pendant subtrees. So that's where actually the important amounts of mass are. There's a diverging number of these pendant subtrees which have sort of macroscopic size, and we know the rescaled limit in distribution of those sizes. And it's also the case that with high probability, no two of the large ones are adjacent. Okay, so you see them sort of spaced out by at least sort of graph distance 2. So we've got two permutations cycles, one which is sort of outside and the other inside the graph cycle here. So here's the inside one and here's the outside one. And each pendant subtree which hangs off that graph cycle belongs entirely to one or the other of them. And for a single such subtree, it's equally likely to be on the inside and the outside. Okay, so here are the two possibilities. So if the relative ordering of the times of arrival of these permutations is A, B, C, then the B will be this side. So if the pendant subtree happens to have the B label, we'll get it on this side. And if it has the C label, it'll be on the other side. Okay, so there are two possibilities. One gives me sort of membership of the inner cycle and one gives me membership of the outer cycle. Pairs of subtrees whose roots are at distance 2 or more turn out to be independent. This coin flip occurs independently for those. And that's basically enough to tell me that what I need to do is just take the masses of those pendant subtrees, with probability of half each goes outside and with probability of half each goes inside. And I just sum up the masses that go inside and that gives me one of the permutation cycle lengths. And if I sum up the masses on the outside, that gives me the other of the permutation cycle lengths. Okay, so I'm not telling you why they're beta 1/2, but for the probabilists in the audience, this turns out to use neat distributional properties of the Brownian pseudo bridge and Levy's arcsine theorem. So you can relate the amount of mass sitting in these pendant subtrees to the time spent positive by a Brownian pseudo bridge. Okay, so I won't go any more into that. So I've got about, I guess, 5 minutes or something like that. I don't want to go too far into this. But so something similar is going to happen for the more complex components. So maybe let me just show you the pictures of what happens. So here's a sort of more complex component which has got 3 permutation cycles involved in it. And we can use sort of graph decomposition theorems. So there are standard ways of decomposing these things into sort of cycle structure and extra stuff, which enable us to, let me not go through all of this, enable us really to simplify this problem slightly down to just looking at what's going on in the cycle structure. But again, we have the property that the vast majority of the vertices are sitting in these pendant subtrees. So we've got this sort of interaction between this cycle structure, which we can actually sort of idealize into things we call trajectories, because it's not really going to matter which of these vertices here is in which cycle. There are very few of them relative to the total size of the object. And then we can just deal with what happens to these pendant subtrees. So we get this sort of decomposition that sort of says that really for a large one of these things, I'm just removing all of the sort of technical details, if I can put it that way. The picture is as follows. We've got a sort of schematic diagram of what the cycle structure looks like. Not very much interesting happens along one of the edges of the cycle structure, but at each of these sort of corners, at least at one of these vertices where things interact, we have two possibilities. There's sort of an orientation for each of these things, which either is sort of clockwise or anti-clockwise. And that tells us that we're essentially coming out of this sort of schematic diagram. There are sort of two possibilities. Either this graph cycle structure is going to give me 3 permutation cycles, or it's going to give me a single permutation cycle that sort of weaves in and out. And in general, for one of these graph components, it's got some graph cycle structure itself. And what's going to happen is determined by what's going on at the vertices of degree 3 or more in that cycle structure. Each of those gets a little orientation, and that's going to sort of tell us how these trajectories weave in and out of the edges of the graph. So a typical component of the Heuristic random graph is going to look something like this. And one can decompose it into the sort of the graph cycle structure and then pendant subtrees. And it's possible to understand how the masses of those subtrees, each of them essentially ends up going one side with probability half and the other side with probability half. And once we put that together with some understanding of how these trajectories weave in and out of the graph cycle structure, we can understand what the sort of scaling limit of the permutation cycles that we put on top of this are. So I'm just going to flip forward a few slides. I was clearly quite optimistic about what I could get through here, so please ignore this. Maybe the picture is the best thing to try and understand what's going on here. So here what you can see is we've got our pendant subtrees. So here's a sort of large schematic diagram of one of these Heuristic graph components. It's got these pendant subtrees which sort of sit with probability half one side of the line, with probability 1/2 the other side of the line. And then on top of that, we've got these trajectories, which at every one of these sort of important vertices of degree 3 or more is making a choice about whether it sort of hops over to the other side or whether it stays on the outside. So here, a particular set of choices has been made. And these trajectories just go around and pick up the pendant subtrees that are on the right side of the edge. And that enables us to give a sort of explicit, well, okay, somewhat implicit description of how much mass is ending up, how much of the permutation cycle is ending up in which part. So this gives us a sort of rather complicated but explicit description. And again, there are sort of Brownian bridges sitting underneath this and another theorem of Levy. So I think I'm basically out of time, but let me just whiz through this and go. Yeah, no, I think that's a good place to stop. So there's a way of putting all of these different things together, can understand not only the sizes of the components of the Heuristic random graph in its critical window, but also what their surpluses are. That's another thing that Alder's proved. And if we put those different pieces of knowledge together with this now structural understanding of how the permutation cycles relate to the graph components, then we can get our scaling limit at the end. And I'm sorry for whizzing through lots of things there at the end.
Great, thank you very much, Christina. It's very nice. Sorry, there is someone speaking in the street now.
Don't worry, that's absolutely fine.
Okay, so essentially, let's clap first. Is there any question? Okay, so let me ask you. So essentially, you use the fact that in this scale lambda, the component of the Heuristic graph is essentially a tree. with
It's
some.
a tree or close to being a tree, yes.
It's almost a tree with some very small cycle components, and then it's very nice that you were able to study the components of the tree with this almost biology, right? You go to each species and characterize what is going on with each of those, and then you have this probability to choose somehow one component or the other. This is what you're doing, right?
Perhaps I can just say a word about what happens as lambda gets large, though, because we do have this phenomenon whereby the largest component is getting larger over time. And eventually this sort of, my representation of it as being something that has only very few cycles sort of stops being true. It starts having a number of cycles which is on the order of lambda cubed. So really what you should think of is the largest component, if I take a very large lambda, is a large 3 regular expander. And one has to try and understand these things for that. And that's really where the Poisson-Dirichlet distribution is coming in.
Okay, so for lambda big, then it doesn't work your representation for lambda to infinity.
The representation works for any finite lambda, and one has to understand what's happening as lambda goes to infinity. And there's quite a lot of work that goes on in that passage.
Okay. Is there any relation with this Polya-Arn, this uniformity?
So can you? I can't think off the top of my head of an urn.
Okay. No, sorry.
No, probably. I'm sure there is one now.
It was something known because there are some relations between the Polya-Arn and these permutations, and so I thought that maybe this uniform cycle distribution is also related to that. But okay, so really very nice and pretty deep to try to understand in just one talk.
Sorry, I was probably too quick.
I don't have any other.
That's absolutely fine.
Actually,
okay, thank you. Yes.
I have a badly formulated question. It's not a question really. It's I'm trying to make sense of it. But you know, there are all these results where they still get the Poisson-Dirichlet limit when they put cycle weights. Just when you take the permutation, but instead of looking at the uniform permutation, you put some cycle weights. And maybe, I mean, I'm just asking if you've thought of any way of introducing dynamics instead of using just the uniform transposition. If you put something that somehow takes into consideration whatever you have in order to split or merge, do you see anything like this coming up?
Yeah, so I think you'd have to have some sort of split merge dynamics where you maybe sometimes at a certain rate you just suppress some of the jumps, say, so that you're sort of managing to get a reweighting of the rates. I think that's the natural way to do it. I feel like there should be some analog of this story that goes through with a Poisson-Dirichlet. You should be able to get 0 theta for a general theta. But to be honest, we haven't quite managed to finish this piece of work, and that's sort of somehow in the background as the next thing to think about, if I can put it that way. It would be nice to have an analog of this story for some of those weighted permutation models, but for the moment, I don't know exactly what the story is, if I can put it that way.
Okay, any other question or comment? Okay, so today for your next thing.
I think if there are no more questions, I think we should thank Christina again, and then I'll stop the recording.
Thanks very much, everyone.